Okay, good afternoon to all of you. Now today we'll discuss maybe two concepts. One of them is the Huffman tree, and second is a B tree. Now, uh, with this two, we'll be able to finish this chapter of trees, and then lastly, which will remain, the graph has to be done, which will take around 5-6 classes, plus the question solving and your problem solving and your doubts. We'll cover it in the next 10 classes. Now today, let us try to discuss the Huffman tree. Now, before we are going to discuss the Huffman tree, we'll discuss one of the important things, which is called the path length. The path length. Now, let's discuss the path length. Now there is one more concept which is there, is the concept of, we call it two tree. Now, a two tree is a tree where each node will have exactly 0 or two children. That means no node will have one child, and such a type of tree is called a two tree. Therefore, what we are going to do, we are going to make a two tree like this, something like this. Now, such a type of tree is called a two tree because you find that all the nodes will have exactly 0 or two children. Now, this is an example of a two tree. Now, why I am trying to discuss the two tree? Because Huffman tree is related to two tree, and therefore all the one nodes which are given in circles are called the internal nodes, and all the nodes which are rectangular are called external nodes. Now here, if I am going to calculate, that means if I am going to understand what the formula, therefore number of external nodes is equal to number of internal nodes plus 2. The number of external nodes is equal to, sorry, not plus 2, plus 1. That means number of external, where n is in the diagram, the internal nodes are the circles, the external nodes are the rectangles. And this formula will hold for all two trees. Obviously, it will not be applicable for general trees, but will hold for all two trees. Now, if I am going to calculate the path length of this tree, now the path length of this tree will be defined as the sum of the distance from the root to all external nodes. Now, in that case, if I am going to find the length of external nodes, now here let us try to find the length of external nodes, LE. Now that means there are 1, 2, 3, 4, 5, and 6. Now let's try to do it for 1, 2, 3, plus again 3, plus 3, plus 3, plus 2, plus 2, will be given by 16. Correct? Why? Because for 1, it is 1 from here. If you take 1, take this 1, 2, and 3. Similarly, you do for all other external nodes, it will be 3 plus 3 plus 3 plus 3 plus 2 plus 2. And the length of external node is 16. Now, similarly, if I am going to find the length of internal nodes, now let us try to find the length of internal nodes. Will be given by, for the, this one is, for this it is 0, therefore it will be 1 plus 2 plus 2. Which is nothing but equal to 6. Okay. Now, what I got two things. This is the length of external nodes, and this is the length of internal nodes. And now, let us find the relationship between LE and LI. Now, can you give me the relationship between LI and LE? Into plus, what should be the formula?
2ni.
2n. Where if I say n is the number of what? Internal nodes. That means where n is equal to number of internal nodes. What you said is correct, is ni. And now this formula will hold for all two trees. This formula will hold for all three trees. That means the length of external node is equal to, now if you compare, if you are going to do this for Li is equal to 6, n is equal to 4, 4 into 2 is 8, and then you add for this, it will come to this value. Okay. No, sorry, n is equal to 5. The 5 into 2 is 10. Therefore, if you are going to, in this example, n is equal to 5, 5 into 2 is 10, 10 plus 6 is 16. Therefore, the number, therefore, the total it is total is equal to 16. And this will hold for all two trees. All two trees. Now, with this in mind, what we are going to do, we are going to find a tree which all those two trees which can be constructed from given number n number of, say, any with given any and ni. Now let us try to define that how we are going to find the two trees like this. Now suppose you are given some values. For example, you are given some values. Suppose you are given the values of say 4, 2, 8, 5, 9, 6, like this. Or let us try to make it say smaller. Let us try to make it smaller, just to make you understand. Then I'll make a bigger one. Let us try to do it in suppose I have to make 2, 3, 5, and just try to do 11. Suppose I have to make a 2 tree with 2, 3, 5, 11. Now, here these numbers will come as an external node. Will come an external node. Now, what I can do, I can make a tree like this. Correct? Or I can also draw a tree like this. That is, suppose I have this, this is also a 2 tree, this is also a 2 tree. Or even I can interchange the numbers. Therefore, in that case, instead of 2, 11 will come at the place of 2, 5 will go to place of 3, and so on. Therefore, in that case, I can do many type of trees. Now, let us try. I might make a tree like this. And this is also a 2 tree. That means with 4 number of nodes, I can make many trees. And those 2 trees, the nodes might be at different positions. Now, the question is, if with this tree, I want to find the path length of this tree. Now, I want to give the path length. Now, in that case, what is the path length for this? It is going to, you are going to multiply the length multiplied by that weight. Therefore, what I can do for this one, I can calculate like this. This is 2 into 2 plus 3, 2 into 3 plus 5 into plus. How? Because for 2, the path length is 2, therefore 2 into 2. For 3, again the path length is 2, therefore 2 into 3. For 5, again the path length is 2, therefore 5 into 2 and 2 into 11. Now, if I am going to calculate for this tree, you will calculate this 2 into 2 plus 1 into 11 plus 1, 2, 3, therefore 3 into 3 plus 3 into 5. How much is this? 15 plus 15, 30, 39. Now, if I am going to do for this, it is 1 into 2 plus 11 into 2 plus 1 and 3 into 3 plus 3 into 5 will give you 22, 24, 20, 33 and 15, 48. Now, the question is very simple. You are given one value. You are given one value. You are given this as one value. And there could be many trees with different values. All of them are 2 trees, but not Huffman trees. All of them are 2 trees, and the minimum of them is the Huffman tree. That means if there would have been only 3 trees like this, the middle one would have been the Huffman tree, and all other would not have been the Huffman tree because that is giving the minimum weight. Therefore, in that case, what I'm going to define, the total weight of is given by W into L. That means you are going to calculate the weight of this tree is equal to P is equal to W1 into L1 plus W2 into L2 plus W3 into Wn into Ln. Therefore, what I'm going to do, I am going to calculate, the formula is simple. I am going to calculate like this. Say, Now, if I am having, suppose if I am having the 4 ones, there will W1 into L1 plus W2 into L2 plus W3 into L3 plus W4 into L4. And if I'm going to calculate for all, it is Wn into L, and where W1 is the weight of that external node and L1 is the path length to that node. And therefore, this is the formula which I am finding. Therefore, in that case, what I am trying to get, I am going to get the P is equal to this much. I am getting P is equal to this much. I am getting P is equal to this much. And in this case, the middle one would have been a Huffman tree, but I don't say it is not an Huffman tree because I have not drawn all the trees. I have not drawn all the trees. I just drawn 3 of them. Now, if you are going to replace, say, if I am putting from, if I put this 11 from here to here, the total path length will change. Total path length will change. Therefore, if I am going to just shift the values from there, I will be able to get different types of 2 trees. Now the question is how to draw a Huffman tree. How to draw a Huffman tree. Now, of course, with 4 nodes it is difficult because you will get lot of trees. If I put you 10 nodes, you will end up in finding maybe 100 of trees. Therefore, there must be some particular algorithm by which you can find a Huffman tree. And that algorithm we are going to discuss is called the HUFFMAN algorithm. Therefore, the HUFFMAN algorithm starts with a 2 tree and then terminates to make a single unique HUFFMAN tree which is having the minimum weight. Okay. Now let us try to show. Now, is it clear to you till here that why I am trying to make a 2 tree like this? Now, with this, let us draw a 2 tree. With a draw a Huffman tree. Now, from the book, I'll take the example so that you will be able to do this. Therefore, these are the weights. Now let's try from the book, page number 7.68 from Shom series. Therefore, I am going to draw like this. Now the numbers are okay. I missed the D, but it doesn't make any difference. I can put it anywhere. Now these are the 8 nodes by which I will be trying to make a Huffman tree. Now here, the Huffman tree is made from bottom to top. The bottom to top. That means I am trying to make a tree such that it grows from bottom to top. Now it is simple. What I have to do is a very simple algorithm. What I have to do is that with this 8 external nodes, I will pick the 2 which is the minimum. I will pick the 2 which is the minimum. Now here, obviously, one of them what you will pick is 2 because that is you will pick E with 2. And the second one, you can either pick P or you can pick H because both are equal, having a weight of 5. Therefore, I can take any one of them. Therefore, it is just your thing. Therefore, let us try to do it like this. I am going to let us take this over here, and I'm going to take over here. These two are the minimum weights, and I will put this as an internal node with the value equal to 5 plus 2 is 7. I will take that 5 and 2 and make as an internal node with 2. Now I am remaining with now only 7 nodes: A, C, F, G, H, and D, plus that internal node 7. And then I will pick the minimum 2. The minimum 2 over here is obviously H and the one internal node which I have just made. Then what I will do, I will make like this, and I will make like this, and make it like this, which is nothing but 5 plus 7 is 12. Correct? Now I will again pick the minimum 2. Now minimum 2 over here will be what? Now you are remaining with A, C, F, G, D, and 12, because 7 you already used. You cannot use 7. Now here there are 2 11s. Therefore, what I can do is that I will be clubbing those 2 11. And therefore, let us take a different color pen so that you will not miss the thing. Then what I am going to do, I will take this 11 and I will take this 11 and make it as 22. Then again I will pick the minimum 2. The minimum 2 is what? It is 12 out of 22, 12, 22, 25 and 19. Now these are the remaining. One is 22 which is remaining, A. Then one which is remaining is G. One which is remaining is D. And 2 internal nodes are there which is remaining is 12 and 22. That means you have to pick the minimum 2 of them. That means what are the nodes? You will have 22A. Then you will have you are having this 22A, and then you are having 25G. Then you are having 19D, and 2 of them 12 and 22. So these are internal. Obviously, you know we'll pick only 2 of them, which is 19 and 12, the minimum of them. And then what we'll do, we are going to make this from here, and we are going to put it here, and put it is equal to 31. Now, of course, this is now gone, and this is now gone. And instead of this, you will have another node, 31. Now you pick the minimum 2. Obviously, you will have only 2 nodes to pick, that is 22, 22. Then what you are going to do, you will use, I'll just using another pen, and I will just be putting like this 22, and this 22, sorry, not this 22, and this 22 will make it 44. And now this is gone, and this is gone. And instead of this, we are having one more 44. Now you pick the minimum 2. Obviously, 25 and 31 is the 2 minimum. Therefore, you are going to pick out of this. Therefore, I'll pick this one. I'll pick the 25 and 31. Therefore, just I will try to use like this, but it might overlap. If I'll put like this and make it 56. And now here, this is gone. This is 25 is gone now, and 31 is also gone, and you are remaining with one more 56. And now you have only 2 nodes to do. one is for 54 and one is 50. Therefore, what you are going to do, you are just going to add this over here and get 100. And you are getting this 100. Okay. Now with this one, this is a 2 tree. Now here, what you find over here, that the nodes might not be looking that good because and the lines are crossing. Therefore, it is just because I have not rearranged the external node. Therefore, it is happening like this. Now, what I will do is that I will just try to make it look more beautiful by just rearranging the nodes. Okay. Now, what I am going to do, I am going to redraw it so that you will look. You start with like this. Say 100. Then you will have 44, 56. Then you will have, with 44 you are having 122, and therefore here you will have 22. This one. Then with 56 you are having 31, and it is having 31 and 25. Then for this 22 you are having 11 and 11.
So why are indicated the right child with the square box?
Pardon, just please repeat.
So why you have indicated the right child with the square box?
Because
44 of 22.
those are leaf nodes, not those are leaf nodes.
Leaf nodes, okay.
Because all those circles are internal nodes. All the rectangular ones are the leaf nodes. That means you don't have any children. Now,
Okay.
just repeat once again that this is a 2 tree. A 2 tree, every node will have exactly 0 or 2 children. It will not have like a binary tree. Any node can have 1 child or 2 child or 0 child. 1 children,
Yes, sir.
0 child, 1 child or 2 children. But here no nodes will either have 0 or it will have 2. Now,
Yes.
if you check with 31, it is 12 is an internal node and 19 is a leaf. Therefore, what you can do with this, you can put 19 as a leaf and 12 as an internal node. Then for 12, 7 is an internal node and 5 is a. Therefore, here I can put. Okay, I will put like this. 7 is an internal node, and for this, and 5 is external node. Now for 7, 5 and 2 both are leaves. Now check how many external nodes are there. 22, 11, 11, 3, 4, 5, 6, 7, 8. Now which are the external nodes? Just for your reference, I'm just trying to put into the ping box. This one, this one, this one. And you see, now this both the trees are same. What I've just done is what I just did is that I just tried to align the height. Just try align the height. And this is a 2 tree as well as an Huffman tree. Now with any other arrangement, you cannot make a tree having the weight less than 100. That means you draw as many trees you want, as many two trees you want, but the minimum weight will always be 100. And this tree is a Huffman tree. And this tree,
So that is how we are supposed to draw a Huffman tree, no? We have stored the whole position.
you are just put your mic a little away from your mouth because making a lot of echo. Then speak.
Okay, sir.
Hmm.
Sir, I am asking, sir, that is how we are supposed to draw the Huffman tree, no?
Of course, because you cannot draw all the two trees and then find the minimum. Because
Yes.
this you might end up in finding maybe hundreds of trees. Therefore, this is given by such that you are going to make a Huffman tree like this. And this tree is a Huffman tree, and in practice, the minimum weight of this tree. Now, if you are going to calculate the weight, what we have done over here, we have calculated these weights. We have calculated these weights. Now, the meaning is this: with this number of nodes, the weight is equal to 100. The weight is equal to 100. Okay, that is P is called the weighted path length. Now here, what I have to write is P is called the weighted path length. The P is the weighted path length, and this means the weighted path length of this Huffman tree is 100. The weighted path length is equal to 100. That means if you are going to draw any other tree, the weighted path length will be more than 100 itself. The only thing what you can do, you can put two on the suppose if I take these two nodes, I might interchange 2 and 5 on the left and right side, but that doesn't make any difference because the shape of the tree will remain the same. Either you can put 2 on the left of 7 or right of 7, that doesn't make any difference to the overall structure of the tree, and that will not even make a difference with the total weighted path length. The meaning is this: if you are going to shift the weight from this place to some other place, obviously it will change. Now, if I am going to put, if I put this 11 and 22, obviously this will make a difference. This will make a difference, and the path length, weighted path length will increase. Okay, got it? Now, the biggest thing you should have asked: why do we use it? What is the use of such a tree? Obviously, at this level, it doesn't look any important. But let us try to. You might have heard a word, maybe in any time. It's called a Huffman code. You might have heard a word called as a Huffman coding. Now, Huffman coding, which is nothing but a coding algorithm, where you are going to develop a code for each and every characters what you transmit from the sender to the receiver side, and that code has been developed by using an Huffman tree. Therefore, we are trying to discuss the two tree, then the Huffman tree, and then the Huffman codes. And therefore, let us try to show you how the Huffman codes are developed, and therefore that is we are doing how to apply. Now, the application of this in coding. Now, this is an important concept, and you have to understand it well. Now, what happens? Now, if I want to transmit a string of characters, how much space it will take? For example, I am trying to transmit we are learning suppose I want to transmit we are learning data structures from the sender to the receiver side. Maybe I have a place like this, maybe the sender, and I am having a receiver, and I want to transmit this line from here to here. Now you tell me how many bytes I require. Come on. How many bytes will one character take? 60. How? How, Ahmed?
30.
How 30?
Sir, 26 are alphabets and 4 are spaces.
Okay. Ahmed, you said 60. Why?
Sir, a character would take 2 bytes, and there are 30 characters.
How do you know it takes 2 bytes?
Sir, it generally takes 2 bytes, I think.
In general, you have to come with a proper logic. A ASCII character. Now what? Now let's come to your. Let me tell you why you are wrong. Now, what is the size of what is the ASCII value of A?
65.
Correct, 65. How do you convert 65 to binary? You have done it. The divide
By regular division.
definitely you will do like this.
Yes, sir.
This is the ASCII value of 65. You know it, 2 power 0, 2 power 1, 2 square, that you have done in the last semester.
Yes, sir.
This is 8 bits. How many bytes? Now that must be very clear to you. All ASCII characters takes 1 byte. And therefore, how many ASCII characters are there on your keyboard? Yeah, how many number of characters you can depict using 1 byte? Yes, 256. Yes. It is nothing but one. It is nothing but 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 will give you okay. Is it correct? No.
255 would be the sum.
Correct.
So
It will be 255. Correct. That's what I wanted answer from you. Now why 255? Because 0000 will give you. That means you can show with from 0 to 255. And this is totally is 256. Okay. That means if I store all zeros, it will be 0, all ones, and this is 8 bit, which is 1 byte. Now it means that each and for to transmit this, you will require what you said may be correct is 30 bytes. Considering that there is 26 characters, alphabets, and 4 spaces will take 30 bytes. Now my question is that how can I make less than 30 bytes? Obviously, you can't do if you are going to represent as a normal ASCII value. That means you cannot do it because you cannot compress the ASCII characters. I cannot compress it because it is the minimum every ASCII characters will take 1 byte. Now, but it can be done if I apply a coding mechanism to this. If I apply coding mechanism. Now, what is a Huffman code? A Huffman code is designed in such a way that each and every character will be having a unique code, and the code will depend on the frequency of that character appearing in a particular data which you are going to send from one place to another. That means the length of each character will not be fixed to be 1 byte, but will depend on the number of occurrence of that character in the data set. Now, obviously, this is only 30 bytes. But if I am going to say transmit, say 3000 characters, Now in that case, what I will do is that I will try to count the repetition of each character and how many times it has come. And with that repetition, what I will be doing, I will be finding a code for those characters which are coming more number of times as a shorter code, whereas those which are coming less number of times is a longer code. Okay. Now with this method, I will be designing a new code which is called an Huffman code, and that code will be less than the normal ASCII characters. Now it was initially used. Why so much? Because data transmission was very costly. Now in the present situation, that might not be a bottleneck. Therefore, that is not a very important concept in today's scenario, but it is a very important concept around 10-25 years back, when the cost of transmission of data from one place to another was very is costly, and therefore people thought of finding a rule to compress the data. Okay. Now you already know that there are a lot of compression algorithms which are there in other fields. Okay. Tell me, which of the compression algorithms you know? Which are the compression algorithms you know? इमेज के लिए बताओ.
Sir, what special gossip?
Which particular compression algorithms you know by name? Compression algorithm, you know what is the meaning?
So sorting.
No. Compression, which compresses the size.
Of sir, linked list tree what?
इंग्लिश नहीं, algorithm बताओ. जैसे कि मान लो कि अगर मान लो हमने ये बनाया, कोई पिक्चर बनाया पेंट में, उसका डिफॉल्ट क्या होता है एक्सटेंशन? अगर तुम पेंट ब्रश यूज किया है ना
सर, यस सर,
उसका जब पिक्चर बनाते हो, उसको सेव जो करते हो, उसका क्या होता है एक्सटेंशन?
.jpg.
नहीं, जेपीजी नहीं होता है, अब होने लगा. इट्स बीएमपी.
पिक्चर का ना,
बीएमपी, बिट मैप पिक्चर, बीएमपी. देन आफ्टर
BMP.
दैट बिट मैप पिक्चर, बीएमपी. It is called bitmap picture. Now that was an algorithm. Now what happened is that they developed the algorithm which is just said JPEG. JPGs to both Joint Picture Expert Group, that is JPEG. Then TIFF. These are all compression algorithms. If you have a size of 1 MB of a picture in BMP, in JPEG it is less than that. Why? Because it's a compression algorithm. It is a compression algorithm which compresses the picture by using some mechanism to compress it. Now, how does BMP works? BMP takes 1 byte per pixel, and the number of pixels you are having multiplied by 1 byte will give you that size. Okay. Whereas JPEG does not do that. Text compression algorithm बहुत सारे आते हैं, आगे तुम पढ़ोगे. Text compression algorithm, जैसे text है. Therefore, those algorithms are the algorithms like a Nath-Morris plot, KMP. Therefore, there are the algorithms which are there. Therefore, there are algorithms that Nath-Morris Pratt algorithm, and there are a lot of algorithms which you will understand, which you do in the algorithm part. Now, the question is,
सर पहले JPG था, आजकल तो JPG फॉर्मेट होता है सर, सिर्फ
ठीक है,
JPG.
उसको JPG लिखते हैं, but उसका JPEG, that is just an extension. Who created JPG? Can you name the person? He's an Indian. Though he did not work in India, working in the US, he was one of the persons there in the group of who developed that. Tinku Acharya, he was the person.
Okay,
A person who worked over there, he developed the JPEG code. He was part of the JPEG code. Now what happens is that, now let us come to the Huffman coding, how this Huffman coding works. The Huffman coding will work like this. Suppose I am having this text, we are learning data structure, which contains, maybe if I find E comes at 4 places. Here, 1, 2, then 3, then 4. A also comes here, 1, 2, 3, 4. Okay. W only comes one times. Okay. G only comes one time. And by this method, what I am going to do, I am going to find the concept like this. Let us try to say A comes, it comes say 15 times. Say E comes say 20 times. Okay. Say P comes say 8 times. Okay, let's do like this. G comes say 6 times. Suppose with these characters you get these counts. A 15 times, E 20 times, G 6 times, K 4 times, R 2 times, U 9 times, and plus all other characters could have been there like this. Obviously, you will have say 30, 40 different characters because you will have all alphabets, then full stop, then comma, and all those characters might be there. They're not only alphabets, you will have a space which comes say 8 times. Okay. Now, what you want to do is that you are going to build a Huffman tree with this. You are going to build a Huffman tree with this. Okay. Now, let me draw it very fast just to show you. I'll take like this Z. I will take this R. Now you show me the tree. Draw a tree.
Sir, you have missed G, sir. 6 miss कर दिया.
हाँ. No, I did for 4, 4. No. This 4 and this 4.
Sir, K की जगह G होगा ना? नहीं नहीं, K की जगह नहीं, K के बाद होगा.
ठीक है ना, ये K 4 है और ये इसका 4 है.
Okay, 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 sir.
Okay. Just I'm just stopping for 2 minutes, 5 minutes, and you because somebody has come.